Hey everyone, welcome back to the lab. In this video, we're going to be doing a brief comparison of modern programming languages, specifically comparing TypeScript, Golang, Elixir, Rust, and F#. So there is no best programming language, but there are languages that are better at certain things than others. So that's what we'll be looking at today. Now, Thea recently posted a comparison of programming languages similar to this on Twitter across several dimensions. And I found it to be a pretty high signal way to compare languages, so I wanted to kind of edit, extend, and reshare it to see how far we could take this thing. And his original post is linked here, and so you can see it's right here. And then this one, I've done a few edits on things that I didn't agree with to make a few things more clear and to obviously add F# to the comparison chart. And so this is what we're going to be going over. We can see that we have the languages on the top, and then we have a few different categories. The first one is around kind of concurrency. And here we see that TypeScript doesn't really have a good use case for this. Golang, Elixir, and F# are pretty good, and Rust is a little bit mixed. The next one I'm calling modern types. And we're saying TypeScript is like mixed. Here, Golang and Elixir don't have this, Rust and F# do. The next one is like pipes and pattern matching, which is really kind of closer to maybe like ergonomics, I suppose, but really just focused on pipes and pattern matching. Here we're saying TypeScript and Golang don't have this, Elixir, Rust, and F# do. Next one's around distribution story, which is really like executables, bundling, how it runs in kind of non-web-based environments. And here we're saying TypeScript is okay, Golang's pretty good, Elixir doesn't really have a good version of this, and then Rust and F# are also pretty good. And then the final one is Windows, but we're just gonna kind of pretend that doesn't exist because I just don't think it's very useful. And so this is it from a high level, and what we're gonna do in the rest of this post is kind of dive into each of these categories and kind of why I think this is a correct interpretation of the current state of the language for this dimension. And so if you're curious about one, if you disagree with one, feel free to jump forward to that section and kind of see like my reasoning for this. One final shout out before we get started is that if you're trying to build full stack projects with F#, you can check out Cloud Seed, which is my F# project boilerplate, and how I kind of start all my projects, and it'll allow you to spin up a full stack F# app in about 10 minutes. Link will be here in the blog post. All right, so let's talk about concurrency. So for concurrency, we're basically comparing how languages deal with multiple processes at the same time. They are concurrent. Now, in theory, this unlocks higher performance levels and more flexible computation patterns at scale because you can do a lot of threads at once. You can make them non-blocking. You can, do all sorts of like tell and then get back. And so theoretically, higher performance, although we'll see that like in the real world, it's actually very highly dependent on kind of the workload and how you build things. And so the rankings here are really going to be based on the overall usability of the system. And so this is going to include capabilities, so like raw performance power, raw ability to deal with these things, but also ergonomics, because I think no matter how good your thing is, if you can't actually use it, then it might as well not exist. So we're going to be trying to make kind of a compound ranking based on that. All right, and so for TypeScript, we're giving them a fail. And the reason is that, mainstream JavaScript runtimes are typically single-threaded. We can think of Node. And so TypeScript does very well for like web-based workloads. The threading doesn't really matter that much. We can often just rely on regular single-threaded asyncs to get past any kind of blocking IO, and that's kind of what Node does. And we see it's like pretty powerful. It works pretty well. But still for this, no mature concurrency model actually exists. And this is an example of where maybe it doesn't have mature concurrency, but it's still quite performant. And so that's why, concurrency and performance aren't quite one-to-one. And I will mention that, JavaScript ecosystem has a ton of libraries, a ton of different runtimes. And so while there's no like mainstream runtime that allow you to do this, there are other methods, there are like other plugins for Node, other kind of runtimes that are trying to achieve this, but just because it's not the typical way of doing things in JavaScript, TypeScript, we're giving this a fail for now. For Golang concurrency, we're giving it a pass. Go has a lot of built-in primitives for synchronizing concurrent workloads, and I personally find these to kind of be unwieldy. I don't really like the idea of channels and pipes and stuff like that. I think it's a little bit too implicit and too much things that you need to worry about for most cases, especially web-based cases. My preference is usually towards like async await. I think that's very intuitive, and yes, it has some overhead involved and maybe a little bit less control, but I think it gives you most of the power for very minimal overhead, which is a better trade-off in my opinion for most workloads. But I will say that, a lot of lower level programmers, especially people coming from Rust, coming from C, stuff like that. They find this kind of simple abstraction to work very well and be better than what they're used to. And so for that, we're going to have to give it a pass for ergonomics. Go is very performant. It has this kind of first-class support for these concurrency workloads, and so we're going to give it a pass overall. Elixir also gets a pass here. So Elixir runs on Beam, which is the Erlang VM, which itself is lauded as one of the best, if not the best, platforms in existence to handle concurrency. And so essentially my understanding is that everything is basically a process and each process is concurrent. And you can basically think of every process as an actor in the actor model. And so everything's concurrent. It's not just like constrained concurrency. And so Elixir just gets a pass simply because it runs on Erlang. For Rust, we're giving it a mixed result here. Now I want to caveat that I don't have firsthand experience in Rust. So this is kind of coming from the experiences of others and kind of their responses on forums and to the original thread of this. And so I think Rust theoretically should be great at concurrency, given its like super speed and advanced ownership models, which theoretically seems like it should work well with concurrency. It should be able to tell you like if you're out of sync or not, if, things you need to check. But in practice, the whole ecosystem kind of seems to be held back by sharded scheduling and async, which means that they're not really tightly coupled, or they're not like tightly, I guess, engineered, so they don't work super well. And so in a lot of applications, this seems to lead to subpar concurrency because these things weren't built to work with each other, and thus under like normal IRL workloads, which honestly deals a lot with async, you're not getting the most performance, the best concurrency story out of this technology. And so due to these kind of general mixed responses from like Rustaceans that actually use the language a lot, we're giving this a mixed, but I don't want to give it a fail because it feels like everything is there to make concurrency great, and I wouldn't bet against Rust. I'm sure they're going to figure it out, but it's just not there yet. Finally, we get to F#. F# gets a pass simply because it runs on .NET, which is the same as C#, which has a very simple, performant, and kind of generalizable concurrency model. This has async await. You can also go lower level if you want with like things like thread pools and dealing with all that stuff if you want. But generally it's just regarded as like a very strong contender here. If you're curious about like F# performance in general, I have several benchmarks, comparisons, things like that with F# versus Python versus TypeScript and versus C# here, if you want to learn more about that stuff. All right, the next category is going to be modern types. And so I've changed this category from the original, in the original post it was type safety, but I changed it to modern types because I think our bar, like our just industry-wide bar for what is passable for types in modern programming languages just should be higher. We're way too accepting of like type systems that haven't evolved in 30 years. And that's like dumb because we have better ways. And so we should just hold all of these languages to a higher standard. And yes, there are still tons of languages that, don't even have types yet, or they have types that like aren't very strong and thus would like, fall below what we would even consider as like just normal types. But I do think that's just like a travesty. It's just like a really dumb thing that's held forward for way too many years because type-safe language just are better than dynamic ones. Yeah, period. That's just what they are. And so, just because we have all these languages that have primitive or very non-existent types, and that's kind of like the average out there, that's the mean, like the mode, like that's just like what most things are. That does not mean that they're good. And so we shouldn't accept that as good. And instead we should expect our technologies to be better. And so that's what we're kind of ranking these languages on in this comparison. And so when I say modern types, what I mean are types that are built in, they're ergonomic, and that they're actually useful. And so in general, I consider a type system modern if it natively has these three things. So the first one is that it needs to have a deterministic and accurate type checker, okay? The type that is actually listed needs to be actually checked deterministically, not with any holes in it. And it needs to not be a lie. Okay, we shouldn't be able to lie to ourselves, because the problem is if we say something is something and we start to trust it, but it's a lie, we end up in potentially a more dangerous place than if we just told it like it is and we don't know what this thing is. And so things like this maybe seem very simple, but actually when we look at things that say that they have types, a lot of them fail. So like Python would fail at this and TypeScript would fail at this, as we'll talk about in a minute. The next one I think is really important is some types. These are basically things like this is this or this. A discriminated union is another way of saying this. And I think this is really important because this is actually a very common thing we have to model. And programming languages that don't have these have to resort to incredible abstractions and kind of domain modeling gymnastics to get at the same thing. And this, in my opinion, is where most of the unnecessary complexity comes from in OO. I think object-oriented programming is fine, but the current ways that we have to model types causes it to lead to too many levels of abstraction, which makes the code confusing, oftentimes non-performant, and kind of falls into the same kind of traps that we've had for like the last 30 years. And so I think some types are very important. They're basically a solved problem. Most modern languages are moving towards it. And so if you don't have this thing, you're just like not a modern language. And so for these things, like Golang would fail and C# would fail because they just don't natively support this kind of thing. The last one is exhaustive pattern matching. And I think this is a crucial part of a good type system because the point of a type system is to help you understand what things are happening and to kind of prevent you from making easy mistakes. And so when you have types, what you're doing is you're basically telling the compiler everything you're going to be working with. And the power of that is that it can help you understand where you've made a mistake. You know, these are guardrails to help you keep you from shooting yourself in the foot. Now, once you've done that with a reasonably good type checker that is reasonably expressive, so you can actually express the types well and precisely, accurately in your type system, then now it can go a step further and prevent you from doing all sorts of potential bad things. And that's where exhaustive pattern matching comes in. It says like you've changed, you know, what I understand the system to do, and now I can show you all the places in the system where you are not covering potential actualities. And I think this is so important to like good systems at scale. And most languages just don't have this. Even the ones with pretty good type systems, they just don't do this yet. And I think this is like very important for like good, long-standing kind of programming languages that are robust and keep people from making mistakes. So that's my rant on that. And then we can kind of go into all the languages and how they stack up to this. Okay, so TypeScript gets a mixed. So TypeScript is almost there. You know, it has a very expressive type system that allows all sorts of advanced type declarations with minimal boilerplate. It allows the discriminated unions. In fact, it's more advanced than a lot of other languages in its kind of implementation of this because you can do discriminated unions on anonymous types with like actual static runtime-based values. Which is pretty cool. But the problem with it is that it's not native. And so it's kind of a bolted on addition later. And this just leaves some gaps between the TypeScript definition of the world and the actual runtime JavaScript definition of the world. And so this means that the type system itself, the ability to model the world via types is good, but there exists a lot of edges where it's lying to you. And so this kind of removes the trust that makes type systems good. Again, if we have good types, but it's actually not true, there's no point in it because we're just saying the wrong thing. And we can't really build a solid foundation of structures and logic on top of that. You know, the other part of this is that, you know, TypeScript is really bolted on to JavaScript and, you know, the tooling has gotten much better over the years, but it still is an auxiliary build step that is not fully built into the language, which is annoying and leads to a lot of problems. And so for this, it gets a mixed because it has some of those like things that we want, but the core type's just like not quite there to solve for the full type experience that we want. Okay, Golang gets a fail because basically it just uses types that, you know, existed 30 years ago, just hasn't evolved really to where we would expect a programming language to be that is modern. And so Golang does have types, you know, they are deterministic, they're not like lying to us. But they're not really modern. You know, without things like some types, we do get pushed towards those kind of OO abstractions to approximate them. And, you know, these are just going to be more complicated and less safe than the primitive typed primitive ones that we would want. And because we don't have some types, we typically lose exhaustive pattern matching because there's no way to tell the type system what all of the possible choices are. And, you know, while there are workarounds, it's typically going to involve things like, you know, an unenforced enum to an object coupling, and there's just like room for error there. And so it has types, they are deterministic and strong, but like they're just not modern. Elixir fails, you know, Elixir does not have types yet, and, you know, types are supposedly coming, but in my experience, all types that are added later to a language rarely work as well as those built in. I think TypeScript actually did an amazing job at this. Like, it's not great, it's not the best, but it is quite good for something that was bolted on later. But if we look at things like Python, you know, types have been there for a while, it's not great. Even things like Clojure, where like, I know a lot of people like it, but it just doesn't have strict typing, which leads to a lot of differences. You need these type spec stuff. Like, it's just not quite there. And so we got to give it a fail. All right, for Rust, we're giving it a pass. Rust is often praised for its excellent type system. There is a learning curve to this stuff, but it really does have great expressiveness, is deterministic, and easily allows for some types, including exhaustive pattern matching, which is excellent. And I would also lump, their ownership model into its type system, that it is a type checker, if you will, just an ownership checker, I suppose, which, as far as I know, is still unparalleled in any other language. No other language does it as well as this does. Finally, we're getting to F#, where we're giving it a pass. And I think, a lot of people haven't experienced F#, but basically, if you like TypeScript or Rust types, F# has the same kind of expressiveness as both of these, but it is trustworthy, so it doesn't lie to you like TypeScript, and it has lower ceremony and complexity to write from Rust. It really feels like writing TypeScript types, but they are real, they are powerful, they are enforceable. And so it gives you the safety of types without that unnecessary effort, which I think makes it a really great balance between the two. All right, the next category is pipes and pattern matching. So pipes and pattern matching are kind of proxies for ergonomics. There's probably a better way to categorize this, and we probably could have like more things we would want to include in here, but this was on the original tweet, so I think we're just gonna keep this here. If you're not familiar with these things, pipes basically allow for the reduction of intermediate variables by piping operations together. Instead of saying like temporary variable A or something, you can just say do this, then this, then this, then this, and then you might save the output, or you might just return. What this does is it kind of further constrains mutability, because you don't have these intermediate steps that could be mutated in languages that allow these kinds of mutations, which is most of them, let's be real. And it makes code paths a little bit easier to read, because there's no extra room for conditionals. It really is just like pipe, pipe, pipe. That's what it's going to do. So it typically makes code more readable. Obviously, you can take this to an extreme and it gets terrible if you go like full point free or something. But I think if you use it, reasonably, it makes code more readable. All right, pattern matching basically allows for safer, more expressive matching on possible outcomes. We do this all the time. If you have like foobar, if else, if elif, switch statements, all sorts of things like this. They're basically trying to achieve pattern matching, which is saying like, I might get multiple values. What do I do on the different values that I get? And so if you couple power of pattern matching with exhaustive matching, you not only get very easy ways to kind of restructure these foobar things, but you also get compiler support for ensuring that you're checking all possible outcomes, which is excellent, because so many bugs come from something changing upstream somewhere else, and that causing the actual outputs of your function to be different, and you haven't handled a case. And so generally these are very good for ergonomics. And here's my kind of like definition of like why pipes are a lot more readable. So oftentimes what you're going to do is you're going to get a value, and then you'll get an output, and then you're going to do more things on that output. It's just a chain of operations, and maybe there's some conditionals in there, but basically what we're doing in any given function is just a chain of operations. And so you could write it like this, but obviously this is bad. More likely you're going to write each of these as a step, and then you're going to have like an intermediate variable, and then you're going to pass it into each other. But this isn't that readable. And then with all of the intermediate variables, we have that opportunity for mutability. We have that opportunity for messing things up or having conditionals. And it's just a little bit more crowded. Whereas with pipes, we're basically just saying like, hey, do this, and then we're just going to pass it into each of these things, which in my opinion is just far simpler, more readable, more scannable, stuff like that. All right, so how do all these languages stack up? So TypeScript fails. There are libraries that allow for pipes and types of pattern matching. I think like RxJS is one of them, but it's just not built in or exhaustive, so it just doesn't get a pass. Golang gets a fail. Golang leans very imperative, like super C-like kind of stuff. And so this whole idea here is like really against this design pattern, and so it really just doesn't have support for this stuff. Elixir interestingly passes. It does support pipes and it does have pattern matching, but I do want to call out that it doesn't do exhaustive pattern matching because it doesn't really have types. For Rust, we get a mixed here. Rust has exhaustive pattern matching, but it does not have native piping, though libraries do exist for this. And my guess is that these pipes maybe aren't as simple for it to implement given the complexities with its own type system and its own ownership model, though I feel like that could probably be ironed out with some fancy typing algorithm, but I don't know. So it gets a mix here. It feels like it could get there, but it's just not yet. And F# here gets a pass. It has pipes and exhaustive pattern matching are built in. And, this example really, it's not full F#, but this is basically what it looks like. Okay, now we get on to distribution story. So for distribution story, we're kind of thinking about three things. The first is kind of like bundling. So like, how does a full app and its dependencies get bundled to run anywhere? So if I want to go from, I have code here, and then I want to package it together and then like get it out to run somewhere on someone else's device or something like that. How does that happen? What tools do I have to do this? The next one is the package manager. So how easy is it to package, distribute, and consume library code to use anywhere? This is related to bundling, but also to kind of like development. So we're kind of talking about both of these because I think they're related. And then the final point of this is like, how does this thing work in non-web environments? We're talking about distribution to anywhere. We often talk about, especially here on the channel, web environments, but we've kind of covered that in the concurrency story. So here we're thinking about like, how well does this work anywhere, particularly in those non-web environments after you've bundled this for distribution? And so let's start with TypeScript, and we're giving it a mixed here. So TypeScript does have the capability to run executables on most OS, and it does have, a pretty good package management system with like, NPM. But the ecosystem is relatively unstable. And, there's always like a few different competing systems. Like, I think it was like NPM versus Yarn at one point. Now we've got like NPM and Bun. And then we've got like several different kind of build tools that we can connect with these things. And then when we actually want to execute this stuff, like, we got to bundle like Node or Bun with it. And then, some of the packages don't work with maybe Bun, or maybe they're not ready to work with NPM. And so there's all this like sharding in the ecosystem that makes it inherently unstable. And like, if you've been in the JS ecosystem for a while and you've had a project and you've left it for 6 to 12 months, it is so likely that you're going to go back to that project 6 to 12 months later and it's going to be broken because the dependencies have shifted out from under you. And so this just generally gives like an unstable ecosystem vibe over time. And so all of this kind of works against it. And let's just be real, it's kind of like single threaded. You're kind of having to package the entire runtime. It's not like super good at these kind of compute intensive tasks because it's just JavaScript. And so it rarely beats out these other non-workloads. And so it's going to get a mix because it can do it, but like there's a lot of asterisks and warnings about it. And so we're going to give it a mixed. Okay, so for Golang, we're going to give it a pass. So Golang has a solid and easy to use package manager, and ability to bundle executables basically natively, all just kind of works. And, it consistently gets good performance across non-web environments. Obviously, it was originally built to be kind of for running web servers, but it's actually a very good system light language. And you can kind of see this in like it runs Docker and stuff like that. Like it's very good in these non-web environments. And so we're giving it a pass here because really this does it great natively. For Elixir, we're just going to give it a fail. So Elixir is really great at web stuff. And I want to kind of reiterate that it's really great at web stuff. And it can do other things, but it's just not the best at it. Elixir has a well-regarded package manager in Hex, and it does have capabilities to export binaries. In fact, I realized that Hex actually does this natively now. But it's typically just not as good as the other options here. And you can kind of see this, like if you go to the docs on native exports, if you go look at the forum answers on like how to do this stuff, they all have very large warnings saying like, you can do this, but like maybe you shouldn't. And so whenever you kind of see that in kind of like the first class docs of something, you have to kind of take a step back and think about it, because obviously like things like Rust and Go, they come with like, of course, we're built to do this. And so I think these things work, but I don't think we should consider it like a first class thing. It's really kind of just an edge case for them. The other thing I want to point out is that Elixir does incredibly well for web stuff. It can really leverage the concurrency and stuff of Erlang VM to do this. Web requests are usually typically not super compute heavy. They're usually more like IO bound. And so that concurrency works really well. The problem is when we get Elixir into a compute intensive environment where it needs to really rely on raw compute, on like raw horsepower, it really falls behind. And so when we're thinking about moving this into like a non-web environment, like why are we doing that? Well, we probably want it to work on like pretty low resources. We want it to work pretty fast. Maybe it's like a data intensive workload. Maybe it's like a low level thing. Elixir is probably just not the best at that. And so for all these reasons, Elixir gets like a mostly fail. Like you probably just wouldn't choose it for this. Next we come to Rust. Rust gets a pass. Rust really was built for this kind of idea that you write once, you can kind of run it anywhere, you can compile it to any target. It uses so little resources that it does everything very fast. It doesn't need that many like system specific things. It was really built for this kind of thing. And so it has a great and stable package manager. It creates excellent run anywhere executables, and it really thrives in these non-web based environments. And so yeah, it gets a pass. For F#, it also gets a pass. And so F# runs on .NET, which has a good package bundling and runtime story. All of these are pretty good. It can do native executables. It can target kind of any kind of machine. It has pretty good battle-hardened packages that are used by enterprise everywhere, and the runtime is generally pretty fast. And now it's not going to beat out Rust or Golang for any of these things. Like, it just doesn't go that low level. It does have more overhead involved, but it does come out very well ahead of most of the others of the pack. And so that's why we're giving it a pass here. All right, the next one is Windows. I just don't think it's really worth talking about because it's basically the same as distribution story. And if we're talking about web-based things, I would just say like use a container and it doesn't matter. You just run it anywhere. So we're just going to skip this section entirely. Next. So there really is no best language to choose, but there are always better and worse choices for a given use case. All of these are pretty good at web-based workloads, but the differences become apparent when you consider other kinds of workloads and how robust you want your logic to be. For me specifically, this is talking about types. I really think types are like a must in any kind of language, any kind of project, especially if you are working with other developers. Now, I personally choose F# for most of my web-based projects as I find it to be a really great balance between usability and capability for most workloads, web-based and non-web-based. So question for you is, what is your favorite language and tech stack for building web-based projects? This will help me see kind of what y'all are using, and if I'm missing any from a comparison like this, I might put them in a future comparison. If you like this post, you might also like the HAM stack, a simple scalable tech stack for building modern web apps fast and cheap. This is kind of the paradigm of how I think about building very robust, performant, full stack projects as a solo developer, and even an enterprise as a small team that wants to be very effective. This is how I think about making them. You might also be interested in how I got interested in F#, my journey through many of these languages and technologies to finally land on F# as kind of a balance between the things that I really liked. And finally, if you just want to spin up a simple web server with F#, you can learn how to do that here on the Giraffe web framework. That's it for this video. Thanks for watching, and I'll see you in the next one.